All right.
Okay.
Okay, thanks. So I'm Dan Massey. This is joint work with UCLA and University of Arizona, and we're going to talk about Prefix Hijack Alert System, or our abbreviation PHAS for the system. Okay, so a basic outline of what we're going to cover. I'm going to talk a little bit about the problem, some observations on the solution space, and then I'm going to present our main system, which is up on the web now, and it's what we call the route views-based PHAS service. So I'll give you an overview of how it works, and I think the more interesting thing is I can actually show you how you can use it now. So in addition to reading your email, you could actually click on the website and give it a try while we're going through the talk. And after we go over the set on the website, one nice feature of PHAS is that there's a great deal of customization, and we'll talk about how you might be able to incorporate local site requirements to make a better hijack alert system. Okay, so the basic problem, in some sense I'm preaching to the choir here, but bear with me for a second so I set the context. We've got concern over BGP prefix origin hijacking. In this case, I have a faulty or malicious AS somewhere. It's going to announce address space it doesn't own. Some sites will adopt this path. They'll route packets to the wrong AS, who may spoof the address, drop the packets, so forth. So, for example, AS52 may decide to originate a path to 129.82.16. One of the challenges here is it's probably not clear to most people in the audience that's a hijack. That is a hijack. That's my prefix. The other AS is my colleague's AS, and they should not be announcing this space. But we all know this kind of problem happens, and that's what we'd like to what we'd like to address. So if this kind of hijack does occur, some routers are going to select the bad route via AS52. Other routers are still going to see the actual route via the real AS, 12145. And more importantly, Colorado State, in this case, the owner of the prefix, is unlikely to see the bad route. Being closer to our own route, we would hope our provider picks us. So we may not know AS52 is hijacking our prefix right now, and that's a real problem. Also, although this is the current set of affairs, please don't add a rule into your configuration saying don't accept a route for this prefix from AS52, because we do collaborate with them, and I can envision scenarios where it might be valid to announce this route. So overall, we have a problem. The legitimate AS doesn't see the path. Anybody can falsely announce the path, and somehow we need to address this. And this is a well-known problem from the NANOG list. In addition to handling prefix origination, there's two very related hijacking problems that are highly relevant and also easily detectable with the same system. The first is suballocation hijacking. So here, instead of announcing the prefix from the wrong AS, I'm going to announce a more specific. Packets will always follow the more specific path, longest match rule. So if I want to hijack part of Colorado State's address space, I could announce the 129.82.138/24. People who see the 24 will prefer that over the 16, and you get part of my space. A much harder problem is the traditional secure the entire BGP path. In this talk, I'm going to restrict protecting the rest of the path to the very end of the path. So the general attack is I can lie about any part of the AS paths. Packets will follow the incorrect path. One thing I know for sure is what's the second to last AS in the path. For example, at Colorado State, I know who the upstream ISPs are. So if that prefix goes from my AS to my upstream ISPs, great. If it goes to somebody else, I can actually detect that and report that as an error if you give me the data. The main problem, of course, is that the prefix owner doesn't see the bad events, and the remote users or remote ASs can't easily determine what's bad without input from the owner or from a signed registry or something like that. So our basic assumption to how to do prefix hijacking is just to look at three main functional requirements. First, if we're going to do anything, we have to be able to see the bad information. And if you look at the system now, we actually can do that. We have data collectors at RIPE, route views, people have private monitoring. So if a hijacking event does occur, there really are the resources to see any significant event. We need the ability to distinguish between good and bad information. That's a little harder, especially if you're running this remotely. The person who really knows this the best is the owner of the prefix. I know what my origins are, I know when they change, I know what my policy is. So the person with the ability to distinguish good from bad, in our opinion, the best person, is really the owner themselves. And then if you see the problem, you know it's a problem, last thing you need is incentive to fix it. The person with the most incentive to fix it is the owner themselves because they're directly affected. They're the ones losing the traffic. So really our objective is just to connect the bad information with the prefix owner and let the prefix owner detect and fix the problem. It's a fairly simple basic concept. So we take data from route views. We start with an initial route table, and then we apply updates as we get them from route views in real time, as near real time as we can get the data off route views. There is a slight delay there. And we're going to keep a database of origins used to reach every prefix visible from route views. Anytime there's a change in origin, we don't declare it good or bad. We simply report it to the interested party. The owner then applies some local rules and says, yeah, that's the change I expected. I added an AS. I changed a policy. Or, wait a minute, no, my prefix shouldn't be originating from AS52, and you have an effective detect. So the main concept here is just collect the data from public monitoring spots like route views RIPE and provide the information back to the prefix owner who can then definitely distinguish attack versus non-attack. I'm going to talk mainly about origin, but everywhere I say origin, you can replace suballocation, you can replace last hop, meaning second to last AS in the path. All right. So that being said, we start off with our basic approach, which is to define what we call a PHAS event. So we take a view from a single peer, one peer monitored by route views, by RIPE, by your private monitoring, whatever you want to choose there. We begin with that peer's initial table, and we say, the peer's origin AS for Colorado State is 12145. We do that for every prefix. As updates come in, we simply track any changes in the origin, and we say an event has occurred, and we log this if that peer sees a change in the origin. For example, I can monitor Colorado State's route via the AT&T peer at route views. Initially, they report the path that ends in AS 12145. There may be a huge number of updates changing attributes in the path, changing some other intermediate parts of the path, but the origin remains 12145 until along comes the attack saying, hey, now AT&T is using a new path ending in AS52. So PHAS logs an origin change saying, as viewed from AT&T, Colorado State's origin changed from 12145 to 52. So this provides our base data, and ideally we would report this back to Colorado State. That seems somewhat plausible because the vast majority of updates you're going to see are not going to change your origin, you hope. But even throwing out the vast majority of updates, the remainder is still a huge volume. So, for instance, we can have a peer that has multiple origins, they're switching between origins. We can see this on the order of thousands of times per day. We can have the peer monitor at the monitoring site losing connectivity, so the origin appears to go away, appears to come back. And a number of oscillations just make this data by itself useful once you've identified an attack has occurred, but too much to send as a detection system. So the next level of aggregation we can do is we can say, let's not just look at the view from one peer. Let's take the combined view of all the peers. Each peer provides a particular origin, take a union of all the origins seen. We call that the instant origin set, the origins used at this instant to reach your prefix. So for example, here I'm using 3 routers from route views. The AT&T router sees Colorado State's origin is 12145. 2 Sprint routers, one in Canada, one in the US, see an origin of AS52. The other sees the origin of AS12145. So the set is the union of those 3 origins. And the set, I claim, is going to change less frequently if you're a multi-home site, if this is legitimate traffic. For instance, the bottom Sprint router, the 14228.241.81, may alternate between AS12145 and AS52, and it may flip back and forth, causing a PHAS event over and over again thousands of times per day or week. The set itself doesn't change in that case. The set still contains 2 origins. And if those are your 2 valid origins, that's all you need to know. So the next step in PHAS is sort of to say, let's track this instant origin set, and maybe that's a valid thing to report back to the user. Unfortunately, that's still a little too dynamic as well. So the instant origin set in some cases may still change dramatically. Most prefixes won't see the instant origin set change unless you configure a new policy, legitimately change origin AS, which for most people you're not doing too frequently. But some people are doing this at a tremendous rate. We've seen, in our data, we've seen some prefixes that oscillate origins literally thousands of times per day. So we had one last approach to kind of get the data down to a manageable level and a level that's hopefully useful for detecting origins. We borrow from BGP route flap dampening, and we say, hey, we can damp the instant origin set. So our objective is to detect a prefix hijack. Our objective is to detect a bad origin coming up. So if somebody announces a new origin for your prefix, regardless of any damping parameter, I'm going to tell you about it immediately. It's going to be added to the instant origin set, and as soon as I get that information, I forward it on to the prefix owner. What I can play with a little bit is when I take a prefix out of your origin set. So every time your origin set changes, I apply a standard routing-like damping penalty. The amount of time I wait before removing an origin from your AS set depends on your penalty value. So if you've changed quite a bit, I'll delay removal by, say, 20 minutes. If you've changed even more, by 40 minutes, by an hour, and so forth. Standard dampening kind of rules. So dampening is going to remove the oscillation you see in the top part of the slide. So initially, everybody sees AS12145 as the origin. We report that as the origin set. Some peer sees AS52 come along, so now we report, new addition. I got to send that immediately. The origin set for your prefix is now 12145 and 52. When 12145 goes away and everybody switches to 52, I delay telling you 12145 has gone away due to the damping penalty. When it comes back, I don't have to notify you the instant origin set has changed. Similarly, 52 goes away. I delay telling you it's gone away. When it comes back, the origin set remains the same. So we can now cut it down to, with the appropriate damping parameters, you really only get the important notifications, the notifications saying something brand new is occurring, and most of the oscillations should be damped away. What you lose is if you switch origins, and you legitimately want to know when your old origin went away, or you legitimately want to know when an attack stops, I may delay telling you AS52 is no longer hijacking your prefix. But once you're at that point, you can pull the data, and you can get that in a more real-time system if you need it at that point. All right. So the resulting system is up and running, and this is just a snapshot of the main page. And what we're doing is we're basically giving you a couple services. Let me jump ahead. So right now, we're using route views data, and we're tracking every prefix visible to route views. We have a set of origins used to reach the prefix. We have logs of the origins changing. We have the sub-allocations for the prefix. We have logs of the sub-allocation changes. New sub-allocation, new more specific pops up, a more specific goes away. We have the last hops for the prefix, and we have logs of when the last hops are changing. If you want to see the current behavior of your prefix, you can simply log on to the PHAS website, click on the query button, and we'll give you the last 24 hours for your prefix. It'll tell you what your current origin is. It'll tell you every origin that was seen over the last 24 hours. And if changes occurred, you'll see immediately when a new AS was added. And depending on how frequently your set changes, you'll see when ASs are removed, subject to some possible damping penalty. If you log onto that and you say, hey, this is actually useful, but I don't want to periodically pull the website to see if I'm under attack, we actually have an email subscription system where you can say, I'd like to get those things in real time. And so you can log on, provide an email address for your prefix. In fact, this is public data for anybody's prefix you're interested in looking at. And we'll email you notifications every time the set changes. So we'll give you an initial set saying, here's the instant origin set for your prefix. And every time something gets added to that set, every time something gets removed from that set, subject to the damping penalty, you get an email notification. If you want to look at a longer-term data, or you want to pull the actual underlying event saying, great, I see AS52 was added, that's not a valid origin, who's seeing it, which peers are seeing that, when did it occur, you can go to the archive and you can pull down the event logs and the more detailed data and hopefully diagnose and fix a hijack attack. What you get if you signed up for the email notification is a very simple text message format. And this is an email I got last night. I just randomly subscribed for a prefix, and it's basically telling me here's an origin change, and the origin set now consists of only AS30533. Nobody was gained, but one origin was deleted out of that set. This is something that's readable by a person, but we aren't really intending this to be primarily for people. We're intending this to be primarily for scripts. So ideally, the script receives the notification, and now the thing we really like about PHAS is now you apply your local policy. So some examples of local policies you might apply. If it's a relatively fixed set, for instance, my prefix, I know the origins, I know they're not expected to change, I know the suballocations, I know they're not expected to change, I know the next top ISPs, I know they're not expected to change. I can statically configure that into my filter and say, look, an alarm telling me that I'm alternating between one of my upstream ISPs, don't bother forwarding that on to me. Just discard that. Other alarms, some origin I've never heard about is announcing my prefix, immediately forward that onto the NOC. So this is a nice simple script. These kind of scripts we'll provide for you if you want to download them off the site. Also, anybody with any knowledge of Python Perl and a little bit of text formatting can build a similar script in less than a day, clearly. More interesting thing you might want to do is you say, okay, that's interesting, but maybe I'm monitoring a prefix that's not my own, maybe an important destination for my customers, and I may not exactly know what the right origins are. Getting the information saying prefix X changed from this origin to that might be interesting. It might also be too much data. You might want to say, instead, I'd like to compare this with name your favorite registry database. So again, a simple policy run on your end allows you to do that. Say, hey, I'm seeing origins that don't correspond to my favorite policy database. This is an especially effective thing if you don't know the origin set, and again is easy to do. The PHAS project itself, for commonly supported problems like a fixed set, consulting an IRR, or something like that, we would provide those guys for you, and certainly we're open to requests for, I'd love to have a filter that does this. If we're not providing that at the speed you want, or it's too much of a custom thing, maybe you don't even want to reveal what it is exactly you're checking, simple text notifications, Python, Perl, or better programming language if you want, and you have your own custom filter system. If you want to do even more aggressive customization, the website provides great data from route views. And we actually ask if you're pulling data from route views, you don't download this yourself and run your own PHAS tracker because it just ups the load on how much route views data is being pulled. I hope we provide you with a solid answer for route views there. But you may want to track your own data. You may want to feed this rather an email system. You may want to feed this into your own internal management approach. So PHAS actually comes as three pieces. PHAS, the thing you see running on the website, consists of an input module, a tracker module, and a notify module. The main module is really PHAS tracker. This guy is expecting, it's listening on a TCP port, and it's expecting to get MRT format messages coming in. Based on those messages, it calculates the events, it calculates the instance sets, it applies the dampening penalties based on what you configured it to set, and it writes to log files every event update, every instance set change, and every notification that would be sent. Then, via TCP, it basically sends the notification messages to whatever wants to receive it. The two helper components here are the PHAS input, which can be customized to take your data, RIPE data, route views data, looking glass data, whatever data you want to feed in, just turn it into MRT format, push it into PHAS tracker. The notifications you can push into PHAS notify. So PHAS notify is simply a program that listens on the TCP socket, receives a formatted, essentially text sequence of strings, and then does something with the notifications. An example of what you can do with the input is, write your own input, and the one we're using on the website we call PHAS input RV. All this program really does is it fetches data from route views and basically plays the data. It's already route views data is already in MRT format, so we just basically play the data into the PHAS tracker. There's a few subtleties about making sure we have an initial rib and that kind of thing, but for the most part, this is a relatively simple program. We're building PHAS input ripe. We expect to have that one up pretty quick. So you want to get the ripe data as well as the route views data, no problem. And we're also working with a particular ISP to build a PHAS input that's not taking data from any public monitoring source, but it's taking data from within their own private system. And all you have to do is get that data, put it into MRT format, feed it into the tracker, and away you go. On the other end, once we've taken that data, calculated what notifications need to be sent, PHAS provides this notification format. The tracker writes them out a TCP socket, and you can accept them and do whatever you want with them. The one running on the website, we call it PHAS Notify Email. So it accepts notifications from the tracker. It looks who's subscribed via the web page, and if a notification comes in for a prefix and somebody's email says, I want to see that prefix, a notification goes out to that email. Just as easily, you can build one that sends a text message, writes to some management software, and we're working with the same ISP to build sort of their custom notify message that when their data system goes through PHAS Tracker, reports an event, it's now going to go into their private management system. So overall, here's sort of our current status. Right now we've got the website up and running. Querying the prefix has been working since July with some early adopters and some private users. I'm expecting, we're hoping that based on now a little more publicity and a wider scale publication, we'll get a lot more trials. We've had the email addresses working in alpha test for quite a while. We made the link public just a few weeks ago. Again, no known issues in the early tests. We're encouraging people for feedback and use. That being said, anytime you roll it out to a larger system, in the back of my mind, I have this fear that right now everybody's logging onto the system and the website has crashed. That should hopefully not be the case. So, work in progress. What we're doing next is basically we're developing and releasing more of these email notification filters. So when you get this nice little text message, you can sync it with the IRR. You can apply it to your fixed set. One issue that we believe is going to come up is better management for large-scale users. So currently, the code is great for somebody like me with a /16 interested in tracking that prefix. Behind the scenes, the code base is tracking all 190K-ish prefixes seen from route views. And certainly, if you have 500 prefixes to manage, you can subscribe all 500. The problem there is really an interface problem and a notification problem. Subscribing 500 will work, but I'm sure people who are operating at that level want a nicer interface, and so we'd love to discuss how we can help do that. We also plan to be releasing the PHAS tracker code if you want to run this yourself. And we're basically looking for feedback on the current system, and if people are interested in using it, what kind of future features would be important for you guys to see. So that's basically the talk, and then if you try it and it's useful, we would love to hear from you. If you try it and it's not useful, we'd also love to hear, what's the problem, what could be fixed. And you can go on the page now. You can also look at statistics and see some of, say, the worst offenders for origin changes and that sort of thing. So at that point, I think I'll just open it up to questions if there are any. Yeah. Uh-huh.
Working in event notification is obviously triggered some light bulbs. Consider integrating that with one of some of the
Mike.
I think.
Okay. Is that on? This is on.
Okay.
Working on event notification obviously triggered some light bulbs on this. You're using email as a notification system. I wonder if you considered and looked at either simple or XMPP, given that at least the former has actually a fairly elaborate filtering mechanism built right into the architecture, which might, at least in some cases, be able to do some of the things that you're looking to do.
Yes, actually we have, and that's one of the notify packages we'd like to produce. For the website right now, we started with email just for sort of a low barrier to entry, sure. But that's definitely a great point and something we plan to look into.
Hey, Todd Underwood, Renesys. So I'm aware of at least 2 existing, and in one case, very, very long-standing system that do similar, overlapping, almost exactly the same stuff, in particular the RIPE MyASN project. So I wonder if you could comment on the relationship between this work and that work. This was sort of a, why did we need another one of these, and what makes this one better, different?
Okay, so that's a good point. There are related efforts on this. RIPE has a MyASN service, and there's a number of other things out there. I think what we found as a distinguishing service here is I'm not asking any provider or any base to actually make the decisions for you. So rather than sort of telling a site, hey, here's the data I would like you to check against. These are my valid ASs. And introducing problems with, well, is that data correctly modified? Was it updated? We wanted to take an approach of, I'd like to get this data actually out to the end user. Whether you want to use it to track hijacks, whether you want to compare it against the fixed list, whether you want to compare it against the policy database, I think there's great trade-offs between all those, and I don't think you're going to find a solution that fits all sizes. So what we were really seeking is an approach that gave the most power and the most flexibility to the end user, and also for some of the ISPs we talked about, we talked with, they don't actually want to rely on an external service. So if you want to run PHAS Tracker locally, here's software that you can actually run locally. You can put it under your control, feed in your private data that you don't want anybody else to have access to, feed in your private system. So there's other great related work on this. I think really the local customization, the local control would be what I'd say is the main feature here.
Hi, Andrei Robachevsky, RIPE NCC. Well, my project was already mentioned here, and yeah, it's very similar to what you're doing. I think you're taking a slightly different approach in that you move this flexibility and power to the client rather than to the server as we do in MySN. We took this approach because we felt that at threshold of installing something, even if it's as simple as procmail filters, could be a threshold too high to start using the system. So we try to capture most useful use cases in standard filters that we provide through web interface. And as you absolutely correctly mentioned, it's a trade-off. And I would be very interested in your experience whether people will opt more for a simple startup and less customization, or these more complex things, and what kind of user groups as well.
Yeah, I mean, I think it's actually, RIPE MySN is, for those who aren't aware, it's a great service, and it really is. But I think we're achieving a similar thing, but I think we've taken a slightly different underlying design philosophy about where the customization lies. And there are good points on both sides there.
Hi. So I could see why you might call this an origin AS change alert system, but I'm not sure why you can call it a prefix hijack alert system, because what about the case where you've got a malicious AS that before it actually advertises the prefix anywhere, it first appends the legitimate origin AS, then perhaps the legitimate, what you're calling last AS, and then prepends itself to the path before advertising it on. In fact, if you've got a malicious AS, you don't know where that AS path started, right? You just know the very next hop.
So what we're talking about here, so we have work that still needs that's still in progress for protecting later in the path. If you use this as your hijack alert system, I can guarantee you that if there's a sub-allocation, more specific, used to try to hijack you, this should see it. If somebody reports a false origin, this should see it. If somebody reports a false last hop, this should see it. If you want to lie about the third AS in the path, yes, this is not going to catch it. But I think there's actually quite a bit of value in catching the, in first catching the sub-prefix, the origin, and then the easy extension to the second hop in the path. So
I don't think you can actually catch an origin from a malicious AS, because the malicious AS who's sitting at the edge could start the AS path however it wanted to.
Right. The malicious AS can lie about the last two hops in the path. Right. Completely make them up.
Okay.
And so that this approach will not will not detect. And we have further work along those lines, but now that gets the reason we're presenting this at this point is what you as a prefix owner can definitively say is, these are my origins, these are not my origins. These are my sub-prefixes, these are not my sub-prefixes. These are my next hops. That gets a little fuzzy when, say, your origin is AT&T and you have, many, many next hops. But in my case, at Colorado State, there's 2. And detecting the rest of the path is a great problem. And this is sort of a step toward that and at least forcing the attacker up there. In addition, many of the events are not necessarily, there's malicious attacks and there's unintentional attacks. And unintentionally, the chance that I append the last 2 ASs correctly and announce the wrong route can happen, but certainly for the configuration errors, I think we catch those, and we raise the bar for the attacker.
Definitely. Okay, thank you.
I just want to add just a little more to what Dan already said to your question. I think it's like, low barrier to entry to detect the origin changes and the last hop changes. The fact is, however, BGP does give you the whole routes. So as ongoing work, we are looking at the whole routes. Just that, there's more work to get done regarding to how you detect valid versus invalid changes. But the philosophy, I think, is the same. That is, we want to provide data to the end users, even regarding the whole path changes. I think the end users will have more power and any centralized decision system to tell the truth from the false.
Hi, Doug Montgomery. Now, Stan, did you tell us how many events the system is detecting a day? Independent of subscribers, just.
So subscribers is in the dozens at the moment,
No,
but we're hoping.
Independent of subscribers, how many
independent of
events
subscribers.
is the system detecting?
So I can give you just a snapshot from the thing up here. So for instance, here I'm tracking origin alarms. This was for a 24-hour period. And based on the route views data, this is a little hard to read, but there were a total of 5,364 origin alarms during that 24-hour period. Of those, there were about 1,100 prefixes that generated one alarm saying, hey, one addition to the set, one notification saying your set changed one time. Even with the damping, and this may be a need to tune the damping algorithm, there were 35 prefixes on that day that experienced between 11 and 20 instant set changes on that 24-hour period. Meaning probably oscillation A to B, A to B, A to B, A to B. Maybe our damping parameters weren't aggressive enough there.
Okay. Did you say you're currently using 3 route view sources?
We're using, so my slide example used 3 route view sources, but right now we're taking the full route views data. So
From how many sources, route view sources? Pairing points, or it's the composite collected data from all of route views?
I'm certain at this point what's on the web is using at least the route views Oregon collector, which is 44 5-ish peers. We also have the other route views data in there as well. So if you extend up to all the route views peers, you're talking small hundred of routers.
As a last question, I was wondering if you've looked at how the number of alarms might be affected by the number of potential collection points.
So interestingly, the preliminary data is suggesting that even with the route views Oregon, enhancing it with route views wide collector or other collectors isn't giving us statistically significant new data. Now that may be, I don't have a long-term enough study there to make any, don't take that as preliminary data at best. So it's suggesting that maybe we have the right collectors. There's a different great question on how do the collectors affect this, and I don't have all the data for that yet.
We're running short on time, so I'm going to cut it off to the people who are currently in line. If you're not in line, sorry.
So I'm not quite awake yet, so bear with me. I may have kind of paused out on something you may have already covered, but this is something that a lot of people have been spending cycles thinking about for a while from different perspectives. And have you looked at I mean, you've got all the data there, but yeah, it's more of like an opt-in kind of notification system, which is cool. You know, that's great. And it's more geared toward people monitoring the propagation, origination of their own prefixes, right?
Right.
Looking at it from the other angle, did you guys give any consideration into like the entire origin set, the entire BGP routing table from a collective AS originating set? Because I mean, there are other people who are more concerned about not necessarily how their prefixes may be originated by someone else, but people who are concerned about, I mean, consider we're working in a destination-based environment, right? That other people's ASs are being advertised by someone who may not be.
So,
do you see my point?
yes, definitely. And
Because I mean, there may be, I mean, this is a great tool for opt-in, but there's a superset of the functionality here that would be very useful to the community at large, just to be able to have some type of candidate subset of suspect originating ASs for certain prefixes, because you may not want your downstreams trying to surf to a bogus announcement. Have you guys looked at the challenges in that? Because I know the original computational overhead is pretty large, but then it narrows down really quick.
yes, and actually what we have, so really for that question, I mean, so just to kind of reinforce your own point, I mean, one use there might be, you know, when I'm looking for spam, it might be interesting to know, hey, this subprefix suddenly popped up 2 seconds ago and has never, but so what we actually have is the data. The question is how to effectively get the data out and do it in the right speed and the right format. We're looking at that. What we have right now is it's easy to pull one prefix. If you want to pull the whole set, the data, the underlying data is there. The data is being collected. Just the right way to disseminate it out, we don't have that nailed down yet.
Are you guys, just sending emails to the authors of the paper? Because I saw the paper when it first came out, and I was like, oh, this is cool. Somebody else is thinking about the same thing. So, are you guys open to suggestions on how to open that up a little bit?
That's we're open to suggestions and collaboration, and we really want to, you know, we're coming at this, you know, as hopefully somewhat clueful, but you know, we're academic research, and the more input we can get from this community, the better I think we can make the tools. So.
What's the avenue of communication? Leisha's email address?
Yeah, there's an email address on the website. That'll get the list that'll hit all of us, and myself, Leisha, Bichuan, everyone. Okay.
Joel Yegley, University of Oregon. Just to be clear, I think the data set you're talking about in the prior question, that's route views 2, because that's the MRT formatted
yes, you're right.
data set that's multi-hop at the U of O.
Right, and that's 45 peers or 44 or?
Yeah, about that.
Okay.
The dump one from the original route views is about 70 at the moment.
Right.
So, and also, I'm still Todd from Renesys. Just to back up your claim, the question was, how many feeds of what character do you need to find all of these? And I just wanted to back up your claim that it's surprisingly few. We've been doing this for a long time too, and for finding unauthorized originations, unauthorized upstreams, partial unreachability, you know, deaggregations, the basic things that people want to alert on, we found that as few as 20 to 40 full tables from relatively well-selected peers catch all of those. So, you know, and going back in time, when we downsample our peer set, that's exactly what we find too, is that you don't need 100 or 200 peering sessions. You actually need somewhere between 20 and 40.
So I agree with you. I'll just putting on the academic hat for a minute. I would restate it slightly as we don't see a significant change by the addition of more peers. I'm missing a lot. Even say I look at topology from a route views perspective. If I try to draw the topology, I'm potentially missing a large number of peer-to-peer links that aren't going to show up there. So I agree with you, but I would restate it slightly as I don't see a benefit by adding more peers. My speculation would be I'm not missing much, or what I'm missing is not significant. But
so yeah. let me restate more precisely. What we did was took our existing peer set of 150 or so full tables and downsampled it a couple different times to look at similar events and tried to see Well, right, which doesn't answer the question of, are we just still missing massive amounts of stuff? But from the existing peer set downsampled to 15 to 50 or so, we see all of, and you're right, for peer-to-peer links, the more the better. You need, many more than 150 full tables. But
Yes, but yeah, I think we're basically agreed. Thanks. Thanks a lot.